So welcome to our next episode of the Motor Doc podcast. So this last week we were at the wind power, or clean power I should say, O&M conference in San Diego. And yet again, we see presentations related to how ChatGPT and related AI is going to save the world and eliminate our need for maintenance personnel and everything else, which I've not ever found that to be the case. In fact, while it does a pretty good job in assisting us in certain things, it is not a replacement for real knowledge and everything else. And in particular, even when, if you look at the screen here and we look at the most advanced of these large language models. Now, I remind you of that, large language models, which most of these are wrapped around. You can see it says ChatGPT can make mistakes. Consider checking important information. Now that's key. I mean, we use it for things like helping us with software development, doing a little bit of extra research. There's all kinds of really cool tools built into these different, what we're calling AI models, or actually machine learning. They are heavy energy users, not on our end. I mean, I'm doing it through basically a browser, but it is a very, very heavy consumer of energy at the other end. So we use it conservatively, meaning I don't use it as a search engine, because what that means is that I'm increasing that carbon footprint that most people seem concerned about. So when you start talking to organizations and they're saying, oh yeah, we use da-da-da-da, and by the way, we're into clean whatever, they're not. Matter of fact, when you start looking at data centers, I mean, cloud doesn't mean cloud. Cloud means this is all residing in a computer somewhere else, usually a data center. These data centers, the smallest one we've been in is about 10 megawatt. The average 100, 200, 400 megawatt locations. They can be quite energy intensive. That's one thing to keep in mind. But what I'm going to show you is some ways that it can be helpful. Things have gone a long way since the release only about 15 months ago. So it's a relatively new technology. And at 15 months, anybody who says they're an expert outside of the companies that actually developed the technology, they're not. There is no such thing. The other thing I'm concerned about is when I keep hearing people being pushed down the direction of becoming prompt engineers and things like that. Well, when it first came out, everybody leapt on board and said, oh, I can create a consulting firm, or I can create a class or a certification around how to enter things in because of how I figured out how to use the technology. What I'm going to show you today is quite interesting. So if I am going to take a set of data, let's go ahead and I'm going to open up a piece of ESA data. Let me get this in the screen here. This is from an EMPATH data set. Actually, I believe this is probably an all-test data set. But anyways, I've got here, you can see I've got 8 channels. Okay, 2 channels are not being used. So I've got 6 channels. Channel 1, 3, and 5 are current. 2, 4, and 6 are voltage. Channel 11 is in watts. And then I see the rest here. The first column relates to a timestamp. Now, it's not actually a timestamp. It's a period of time. So between 0 and this first one, that's 0.083 seconds. Okay, so that would give me an idea of what the sample rate is for this. Now, if I'm doing this from a data science standpoint, and this is the information I've collected, and I'm not using the original software to go through and do all the analysis, say I just have this data dumped, and I need to go through and figure out different things from this data. As a data scientist, the first thing I've done is switch this over to a CSV file. Okay, so basically an Excel file. I need to know some information. What is the sample rate? What is the line frequency? What are other things that I can pull out of this? There's ways of doing it utilizing code. Say I use either Python or MATLAB primarily. There's other systems such as R and even Excel. You can use Excel. Matter of fact, most data scientists, when you're prepping your data, which is 90% of the work, by the way, you do this. We can utilize some of these LLMs to do some of that work for us. So I have this raw data here. I'm going to provide some very basic information, and then I'm going to allow ChatGPT 4. I'm not going to use one of the wrappers yet. They have a number of wrappers for doing research like this, for doing the data science portion. I'm going to do that separately. We're just going to use raw ChatGPT. Now remember this, it's ChatGPT 4, and I'm using the paid for version. It's very difficult to use it with the free version, but you can do some. So in this case, well, as a matter of fact, speaking of that, I should have probably pointed this out here. You see this one here called Analyze Data. Well, Microsoft has their versions of AI and everything else. This gives us the ability to do that as well. Not going to cover that in this session today. We'll cover that later on. So if I'm somebody who needs to do some of this, well, the other thing I need to understand is I need to know a little bit, because the LLM is going to lie to me. It's going to lie a lot. I need to determine when it's hallucinating and when it's telling me accurate information. So this is our data set. It's a pump test data set. This is from years past. There are certain conditions going on with the machine. I'm not going to fire that up. Let's go ahead and allow ChatGPT to show us what's going on. When we're done, I'll show you the EMPATH results. So let's go ahead, and we're going to come down here, and this little thing right here allows me to import the data. So here's my data right there, that pump test CSV. Go ahead and open it. Now it's going to take a few seconds to upload, as I've talked about in the past. The system I'm using to record this, hopefully I'm not lagging too much, does take up a little bit of memory. So there we go. The pump test CSV is up. It's, 12 to 20 megabytes if I remember right. So in any case, I've got this up. There's my data. Now I can say this is electrical signature analysis data. Okay, so that kind of gives it the prompt of what it is, and it will actually recognize it. Channel 1, channel 3, channel 5 are current, and channel 2, channel 4, and channel -6, remember what it looked like. Now there's spaces and stuff in there. These are all things that normally have to take care of when I'm actually doing the direct work. If I was doing it directly in one of the Pythons, like a Jupyter notebook or something like that, for doing my visualizations. Okay, those are voltage. Channel 11 is kilowatts. Okay. Line frequency is 60 hertz, is approximately 60 hertz. Now, I know this from looking at the data before, and the sample rate is either 10 kilohertz or 12 kilohertz. Okay, let's go ahead and review waveforms and spectral analysis to determine any anomalies. First, I forgot something. I like to put it in order. First column is a timestamp in seconds. Okay. Obtain from timestamp. Ha ha ha. See, shortcuts. So you want to give it some detailed instructions. So we're reviewing, and also determine line frequency harmonics, okay, in voltage and voltage and current, in values and percentage of fundamental. What else do we want to know? Let's see. Well, we're not going to get into speed and everything else yet. That we can actually do later, because this is going to remember what we're talking about. That was a big step forward. I can turn off that memory. I can do other things. I've cut off the left column because I've got projects in place right now that we're doing. So let's go ahead and send the message. Now, it is going to do the data science for me. It is going to do all of the cleaning of the data and everything else. It's going to take some time, so I'm going to meander on and chat a little bit and have a little Death Wish coffee out of my RDI Technologies cup. Thank you, Jeff and gang. I've had this now for a few years, and when I drive around, it keeps it warm, especially when I'm driving around doing motion amplification. So here we go. It's saying, we'll confirm this, we're going to do this and that. The next step in the analysis, it's saying, here's what we're going to do. And now it's going to go ahead and do that work. Now, if I leave stuff out, it will take longer to do each step. Now, in this analysis, when I come down here, if I were to open this up, it's going to give me the code associated with it. Here's the first error, and it's saying, it appears I made an error in referencing the column name for the timestamp. Let's correct this, and it's going to accurately identify that timestamp column and then calculate everything. And so here's the corrected code. Now, I'm not going to interrupt it, but after it's finished this analysis, or this portion of the analysis, we'll go back and we'll take a look at some of that. And that means that that's information I can pull out of this and put into Jupyter or whatever other system I'm using, especially when it gets to the end, if it looks accurate. Now, it might look close to accurate sometimes, and I might say, you know what? I need to do more analysis. I need to go in and make some corrections. Well, what I do then is I just take that code out because I understand the code. That's key, understanding what you're doing. And I can take that information then and go through and maybe spread things out or look at a section of the data, etc. Now, I can ask it to do that, but as you can see, this is taking some time. Part of that's deliberate. In reality, this could be doing this all instantaneously, but they drag the time out so it's not just flashing on the screen. So while we're waiting, it's doing stuff. Okay, so it says, so it came out and it said it's not 12 kilohertz, it's 11,990 hertz. So it's close to 12 kilohertz as suggested. Now it's going to go ahead and plot the waveforms. As you can see, I haven't done anything else. I've given it instructions. Now, a year ago, I would have had to have done this step by step by step and had to deal with all of it. But it's going to start out and it's going to identify some of this, and I'm going to basically let it run and see what's going on. So then I can go back to and see where the errors are and everything else. These are all new features built in. And again, this is the raw ChatGPT. This is not the other sections where there are wrappers that are meant for data science that are built right in. Okay, so as you can see here, these are my current and voltage waveforms, and you can see that it has basically just taken the whole set, right? Here's my time in seconds. So this is the lower frequency data, the higher frequency data set, which is 9 seconds. So it's looking at a much larger spectral analysis. So let's see what it comes up with now. And as you can see, it's still chewing its way through. Now what I can do later is I can tell it, hey, I want to see the first 0.05 seconds of current and voltage for each waveform. I could have it overlay each other, all that stuff. I could tell it I want to know the power factor relationship between voltage and current. Now I might have to go back and tell it how I want it to do that if it can't determine it on its own. But in this case here, okay, here it goes. It says, okay, we did it. There's some kind of structural issue with the FFT. Well, it's trying to do the harmonic analysis. It's going to go back and it's changing the type of the way the data is managed. Now, normally this would be done on my PC if I were doing a Jupyter notebook, or cloud-based systems if I was doing a cloud like Jupyter Lab or one of those. Now, if you're not aware of what those are, don't worry about it. That's just a Python, what's called IDE, or basically the programming portion. Here we go. So here's our spectral analysis. And you can see it's taken out a lot of the noise. Okay, so here we are, and it's looking at that. So it's saying, okay, there's our channels. I'm out to 6 kilohertz, okay, because I'm close to 12 kilohertz, right? Now, it's done this as a spectral analysis, and this peak is very high. The other peaks are missing. Okay, so it's now going through and it's trying to pick up on harmonics. That's interesting out here. I'd be interested to see what that is. Is that an issue going on with the machine? Is it something else related? That's voltage, so that's incoming power. I've got a small secondary peak there. I can ask it also to shave that down to a much closer area. And I can tell it to do a bunch of things as far as an FFT goes. This is way too clean, meaning I'm not really seeing my noise floor. So that means what I would end up doing is saying, hey, I'm not seeing a noise floor here. Can you switch this over to decibels with whatever the peak value is as 0? And then it would adjust that. Yeah, basically real electrical signature analysis that I can perform from raw data in a large language model. There's other things I can do with that too. Now, the funny part is how many people are going to run out after this and try to develop their own. Well, again, like I said, it requires a lot of background knowledge to be able to say something is accurate or something isn't. I can even, though, and we've done this as well, understanding the data, I can take in large lumps of data, and this is actually what we do with our monitoring systems, is we will look for anomaly detection. That we're going to cover next week. Anomaly detection and how to take some of this data and use these tools that are available to us to do that work. So it's now calculating everything. Now this was all this just very simple paragraph back here and a simple set of data from an ESA device. And it's almost done. It's thinking. But I have a lot of stuff out here. So, I should have limited it to, say, the first 1,000 hertz or 1 kilohertz, but we'll do that when it gives us an opportunity to type next. This whole time, where are we at? We're at 20 minutes now. This has been analyzing this set of data without any additional input from us other than the first paragraph and us putting information in. Now, can I do this with more complex systems? Oh, yes. Yes, you can. So if I took all of the inputs, because we do this with our MDM programs. So we will get all kinds of power quality information in, and I can take the raw data over a long length of time, toss it in here and say, hey, I want to know this, this, and this, and see what it comes back with. It is taking some time, so we're taking up a lot. Here we go. That's okay. Let's do this. So we're going to say, yep, that's new, by the way. That's something that wasn't there before. So it is basically going to show me the Python code that it developed. So as you can see, it's developed some Python code specifically for this. I can copy that code, put it in somewhere else if I want to use it for other things. Okay, so here we go. This is the first part here. It's saying define harmonics for this, fundamental frequency, number of harmonics, so it's going to go out to 10. Okay, so it set a limit itself. And let's see, here we go, if any equal, the double equals line, if it equals 1, fundamental, so basically that will be the fundamental frequency. I'm going to go ahead and pause while I'm waiting for this to finish analyzing, and then we'll take a look at the data, because otherwise we'll be a little bit. It's 10:23 right now. Okay, so as soon as I had put it on pause, it's still 10:23. They ran into a problem with the data. It prevented them from completing an analysis, etc. Okay, so let's go ahead and we're going to do something else instead. So, oh, by the way, here's when I checked that box, here's basically what happened. So here are the errors that occurred. Here's all the different stuff, like here's the code that created this and so on. So we're going to tell it now that we want you to view, the kilowatt waveform. Okay. Also, show the first 0.05 seconds of waveforms for it'll correct errors. It'll read your intent, by the way. Show the first 0.05 seconds of waveforms in voltage and current. Lay voltage waveforms over each other and current waveforms over each other. Now, if this works right, it's going to recognize how I defined the channels before, and I won't have to give it any other data. Okay, so unless it comes back and it says, hey, that didn't work, then I can add that stuff in. Calculate the power factor related to the peak voltage and we'll leave the error in, and current related voltage and current with channel 1 and channel 2 representing one phase, etc. Okay. We'll do this first. And then let's go ahead. Why not? Let's do as many operations as we can. Display an FFT of the first 1 kilohertz. Okay. In dB, minus dB, with 0 dB for voltage and current, starting at the top. Okay. Starting at the top and counting down. Okay, so the peak voltage or current FFT should be set equal to 0. Okay, so let's go ahead and let's see what it does. Now, it may run into errors, so it's going to see, it said let's tackle these requests step by step. Okay, so lastly, so first we're going to plot the kilowatt waveform, just so we can see what it looks like. Now, there we go. So this is, as you can see, it set the channel, and as a matter of fact, it identified the spaces. Now, this is a common problem that we have to deal with when we're doing Python programming. We have to go in there and eliminate those spaces. So what it did is it said, okay, we're going to do this. We're going to change that label to kilowatts, channel 11. And you can see that it dropped out the spaces. Now, if it shows an error, it probably miscalculated the number of spaces here. That's a common issue that we run into with it. So let's see how long. It shouldn't take too long. Yeah, so I'm figuring we'll probably have another 15 or 20 minutes of this, because I do want to have it go in and see if there's an actual pattern related to the machine. And then, of course, I'll pause this, and then I'll pull up the actual FFT data, or the EMPATH data. Again, it's just taking its time because it's got to, well, we're actually sharing space on the servers, and as a result, some of the lag may be that it's Sunday and a lot of people are playing with the stuff. They now have Sora, which is the video thing. It's not available to the general public, but those who are utilizing that, they take up a lot of engine right now. So come on, let's see. Can't take that long. Now, if I had this in my system, it would be a couple of seconds and then done. Because it's just showing here like it's almost finished. So what would end up happening is as soon as I would pause the video, of course, right? I'll give it just another second or two, and then I'll probably pause while we're waiting. So actually, in the meantime, let's go back up here. So here's an example. So view analysis, if I click on that, this shows that analysis portion here as a separate thing that I can copy and take out and everything else. Oh, it had ran into an error. So it, you can see that this had the short code here. So when it ran into the error, it said, you know what? I need to make some other changes. So it added in pandas, It added in matplotlib, and these are common tools that we use for data analysis. And then it reread in everything. It identified the time. It identified the channel again. This is where it says .plot and everything else, and all the legends and everything. This goes with matplotlib, which is pyplot, which is the graph that we'll end up seeing. Now that all has also a built-in FFT capability. All this stuff is built right into Python. If you have the ability to, you can also do this in MATLAB. Like I spend upwards of like 10 grand a year for single license for MATLAB for some of the studies we do. So I don't recommend it for general anything. Although if you're a student, you can get the student cost, which I should probably do, seeing as I'm working on my master's in data science finally. Just because, why not? Okay, so we'll go ahead and pause, and then we'll go through what it did as soon as it comes back. Okay, so it did take a few minutes, but here we go. So we pull it up, and here is the kilowatt analysis, and you can see the values here. Now, I can, again, just like everything else, switch this over to an FFT, which I hadn't thought to do as part of the description, but instead of stopping this, we'll go ahead. So the next thing is we're going to take a look at that first 0.05 seconds of voltage and current waveform. So here it is. It's now set a time, and it's going to do something similar to what we have back here. I will note as well, by the way, you can save this. You can also download the image. You can do other things with it and so on. So you can actually, and you can even right click on it, save, and it will save the data. It'll save that image. Everything's yelling at me. We're not going to save that right now. But in any case, we can do all of that stuff with all of this. If I'm building if I'm going ahead and building a report or whatever, or a PowerPoint presentation or something I want to put on LinkedIn or whatever else. So let's see what we're up to here. As you can see, it had originally ran into an error. It redid everything. It's basically telling me it's running matplotlib. By the way, I can only do so many actions in a 4-hour period. So hopefully I'm not going to overburden it. That's the other downside of this. So time less than 0.05 seconds. Let's see if it manages to do anything. Size of the figure. Let's see if it understood what I asked it to do. Here we go. Okay. So part of the reason I had some interesting stuff going on, as I can see here. So part of the error I may have gotten is this is actually a VFD. You can see it's all in a PWM type thing. Now that I have them laying on top, and you can see the noising in my waveform, right? So this is my waveform. Interesting. So, I just grabbed this today. I didn't think anything of it. So you're exploring along with me. So this is a VFD application. Voltage on top, current here. Now it's going to go ahead and see if it can determine the power factor. It will probably run into an error because of what the voltage waveform looks like. So let's see what happens. I can go back now, and I don't need to go back because it's on step 3, calculating the power factor. Let's see if it's able to do it. You notice it's doing power factor 1, 2, and 3. And how is it doing it? Peak current 1 divided by peak voltage. If peak voltage, if there is something else, it's 0. Okay, so it's already building in error handlers. What happens if? What happens if? What that means is that the LLM has run something like this before, or has been trained off of something, or has seen something in its training data. What I learned before was the LLM, when I was doing some research, when I asked certain questions related to this type of stuff, it kept bringing up my papers, so and my presentations and my videos and all the other stuff on electrical signature analysis. So it's interesting in that it's doing some of this. Plus, before, when I was doing some articles, I was showing people how to develop the code behind some of this, so that's available on GitHub and some other places. And that's where, by the way, GitHub is one of the primary areas that they use for training data for some of these LLMs, because the license there allows it to be available to everybody. A secret of programming, if somebody else has already done it, don't worry about it. Oh, okay, so it did do it. So the power factor for phase 1, 0.69, phase 2, 0.69, phase 3, 0.688, and you can see this goes out quite a ways. So now it's going to go ahead and do that first kilohertz in dB for me. And here's the programming. I used to have to do all this manually, so it's kind of nice. So it defines a function for me and the inputs for that function, and sets up the FFT, and it's doing it correctly. So my current is 20 log 10. Let's see. Okay, so it's doing both voltage and current as that. So we'll see how that comes out. Meantime, you can see that this is sitting here showing that it's running. I could say if I saw it going south, it's not doing what I want it to, I could stop it right now, go back, edit what I wrote, and then have it run again. So let's go ahead while we're waiting. Now, what would I do here? Well, I would then take these, figure out the average. That would be my actual power factor. Now, this is not true power factor. This is the apparent power factor. So what I would end up doing elsewise is I would have to tell it what true power factor is, how to deal with the harmonics, how to deal with those waveforms, and then have it run then. But for what we're doing for this, this works out pretty well. So it had an error, said, oh, this did not work, it was not aligned properly. We're going to change the code to compensate for that. Let's see, counter an issue related to handling the Panda series data similar to a previous step. To ensure compatibility, we'll convert it over to a NumPy array. So they're now changing it over from basically the CSV or then that imported to a table. They're now converting it over to an array. That array can be handled more readily as an FFT in the method they're doing. And of course, I have them converting it over to dB, all as one function. So yeah, so they added in a couple of lines here, and we're getting close again. And let's go ahead and pause while we're waiting. Okay, so it took a few minutes, but you can see right here it's come up with the FFT. So hopefully it doesn't take too long, but what I'm going to do is I'm going to bring it in closer. Now, I'm not sure why I have this peak right here, which, but we'll be in relatively close to it. More than likely it has to do with the waveform. So let's take a look. I don't remember the speed of the motor, and I'm not clear on what the line frequency is because it's on a VFD. So what is the frequency of the highest peak? Then close in on, say, 180, 0 to 180 hertz. Let's see, let's use a round top. Let's use a Hamming filter. So let's go ahead and see what the line frequency came out to be, and then we're going to go ahead and have it do the rest. So I want to know what that highest frequency is, because it's on a VFD, so it's not going to be 0. But my highest peak right here, whatever this value is going to be that. Now I could go in, if I wanted to, and say, you know what? Instead of using some of the other things back here, like matplotlib, I could say, hey, I'd like you to do this as a plotly, and you know what? We'll try that, because a plotly will allow me to interact, so I can zoom in and see things, highlight, and label if I wanted to. I'm not sure, and I haven't done it before. I'm not sure if it'll work on here, but again, like I said, what you're watching here is some of the stuff we do is in data science. I think what we'll also do in a later one is we'll take a look. Let's say I have my utility data in 15-minute increments from the utility. I would be able to go in and use this and start chewing up that data, time of day, all kinds of things, in order to help me identify opportunities in a facility. As a matter of fact, I can even have it run simulations, projections, and a lot of the things we do in measurement and verification right in here. So, when I'm on stage, and I was, the last question we had at the, I was doing a gearbox presentation, and I was asked about electrical signature analysis and everything else. So that was part of that presentation in a panel on evaluating gearboxes and main bearings. The question from the audience was, how do I see it from AI? And I said, well, AI itself is not particularly accurate, but it's not actually AI that's being used, it's machine learning. And the concepts that are being utilized for doing that troubleshooting, are basically anomaly detection, and then some will attempt to use certain other things. Okay, so we're not actually at 60 hertz, we're at 45 hertz. So that is part of the reason we had errors early on. So, this is stuff I should have done early on. I didn't think to do it. So now we're going to go ahead and we're going to take a look at that FFT only out to 180 hertz. So that's going to give me something that's going to look relatively close to the other. I'm in the 9-second range, so I don't have my high resolution stuff. So we should be looking at peaks when we're using the Hamming window. Should be looking at peaks that are within, say, 1/10 of a hertz, maybe a hertz. I'm suspecting we're going to be in the 1/10 of a hertz range. So let's go ahead. I'll pause this because it's going to take a few minutes. Now, it was able to do it in that first attempt. So you can see we're in now at about 180 hertz. Again, this peak here is most likely related to everything else. But as you can see, I'm looking at dB down. I'm looking at a minus 75 dB noise floor. You can see a lot of peaks in here in voltage, and you can see related peaks down here in current. So we're already starting to see some stuff. Now the question is, I don't remember what the line frequency is the running speed of the motor is. But let's say, let's assume it's 1790 RPM. So let's say the motor is 1790 RPM nameplate. Okay. At 60 hertz. Put vertical lines in the FFT showing the actual running speed at the line frequency on the from the data at the frequency at the line frequency. Note that the data is from the output of a VFD. Okay, so that it may not recognize that. Don't know, don't care. But what we're saying is, okay, adjust the speed accordingly. Let's see if it can handle that. And let's see if it'll put the lines in place. Okay, so here it says, the actual running speed can be inferred from the fundamental frequency so basically it's explaining what it's going to do. So it says, okay, nameplate speed 1790, measured line frequency 45.96. Then it's figuring out the nameplate speed from that. And so basically it's taken the existing data that we had it calculate earlier, and now it's running everything again. And then it's going to run the FFT. You know what? Let's do something, though. We're going to stop it, like I said we could do. And we're going to, because we know what's going to happen here, plot out to 100 hertz. Okay. Then yeah, let's do that first. Then we'll do the other. So let's go ahead and do this one first. As you can see, whoops, it's saying there's an error regenerating. Let's go ahead and hit it again. So we've changed it, and now we've said, okay, we want you to go through and go ahead and do it. So it's thinking through right now. I'm going to wait, and then we'll pause as soon as it figures it out. So here we go. So it says calculate the running speed, do this. So you can see each time I run it, it does something different. So in this case, it's going, hey, wait a minute, let's see, let's use the actual line frequency. You can see that a lot of this is very different than the previous one. Here's the main thing, 0 to 100 hertz. Now I'm going to go ahead and pause while we wait. Okay, so it did run. And by the way, the total time took a little longer than I expected, but it did run. But I'll note one thing here, and you notice it followed my instructions exactly. Now, I'm experienced with ESA, so I made an error, and I said put vertical lines, the actual running speed, the line frequency. What I should have done is, and we'll go ahead and do it, I should have said plus and minus. So I would have been here plus and minus. It would have shown those peaks there. Now, it's just over 20 hertz. We're about 45 hertz here. I'm not seeing a significant peak on either side, so I don't have a running speed peak. But I'm going to go ahead and I am going to change this. Okay. So go back here and say, I could carry on and redo it. Yeah, okay, so actual running speed, so put vertical lines, these should be at plus and minus line frequency. Okay, so let's see if it's able to figure that out. I'm going to go ahead and save and submit it, and okay, so and then regenerate, and then I am going to go ahead and pause this because it's going to take about 10 minutes or so. Okay, so it added in a bunch of code, and it kind of fell apart a little bit. We're still here now. It's showing a line frequency peak, and and showing the actual line frequency. It's showing the running speed on a separate graph instead of plus or minus. But we'll forget about that for now. Chances are we're not seeing a significant peak there. Now we are seeing some stuff related to what might be, rotor bar stuff or something like that, or it's following along these peaks in voltage. But let's go ahead and let's see what it says. Vertical lines, the actual line frequency. So it misinterpreted what I said, or I didn't write it exactly correctly. It interpreted what I said. I didn't identify it correctly. So these are some of the things that you learn as you work with this. Now let's go ahead and we are going to run the full voltage and current spectra as in dB minus dB as above using Plotly. Okay, so let's see if it'll do that. Also run an FFT in linear kilowatts using Plotly. So we'll hit enter there, and let's see what it decides to do. Okay, here we go. It's pulled in Plotly. So it has Plotly available to it. It's going to go ahead and do the channels. There we go. It's saying what it's going to do, saying how it's going to do it. And not sure if it's going to allow the interaction while we're in ChatGPT. But as you can see, here's all the information. It's going to take a little bit, just because we're going a little longer than I planned. Total time so far, by the way, is over 90 minutes to do what we're doing so far. So let me go ahead and pause this. Okay, we've let it go now for about 20 minutes or so, so it's not, this point doesn't seem to be wanting to manage Plotly. So I'm going to stop this. Or not. Okay, I'm going to change this here, and instead I'm going to say review the FFTs and identify any potential conditions using electrical signature analysis, using electrical signature analysis. Focus on current signature analysis, reference signatures from the internet. Okay, so let's try this. Oh, it's not going to let me do it yet. Still trying to analyze. Where's my stop? Huh. Okay, I guess we're going to have to let it run. I will go ahead and give it a few more minutes, and then we will try running this. Okay, so I had to basically stop it. It just said stopped analyzing. So let's go ahead, and we're going to continue. Now, I've shut it down. I've restarted it. So let's go ahead and ask the question I asked before and see if it'll do that. There we go. Okay, so review the FFTs and identify any potential conditions using ESA. Focus on current signature analysis, reference signatures from the internet. So it's saying based on can be identified, common faults include these, that, and the other thing. Around the, okay, so this will give me a link to where it got that data. Don't know where that is. I'm going to say perform we'll try it again. Perform analysis on supplied CSV file and analysis above using line frequency, using motor speed as 1790 at RPM at 60 hertz, line frequency connected to a pump. Okay, so I'm basically giving it some very rudimentary information. I haven't identified anything in particular, so it's now taking a look, and it keeps defining. It's not actually analyzing anything. Okay, analyze the data above. So either we've stopped, okay, so all it's doing right now, it's just defaulted back to defining things. So this means that in order to perform an FFT analysis with the ChatGPT, I can either sit here and wait for this, okay, to work, right? So I'll come back here, say edit, save and submit, and then see if it'll actually do the plotly, and then perform my analysis manually, right? You notice that when I do that, it chopped off everything that I had put in after that point. So I'm going to go ahead and allow it to, okay, to plot the FFT in linear scale. You would first supply the FFT to the kilowatt data. These examples, okay, so it lost the data. So we're going to have to go back to, where's my desktop? We're going to have to go back to this pump test data. Because it dumped the data, basically. That's probably why I had problems when we were running the plotly. So we're going to go ahead and upload this data. Okay, so basically I'm saying read everything we did above, use the attached data. So let's see if it can manage it or if this particular analysis has fallen apart. That does happen, and you could lose hours. I mean, we're already now almost 2 hours into playing with this data. And it's run into some kind of problem. So let's go ahead and try it again. There we go. Now it's saying it's going to load the file, it's going to it's going to compute everything, it's going to use Plotly, and then here we go. So not sure where the Plotly is, but it must be doing that afterwards. So there's the FFT and everything else. I'm going to pause and allow it to run everything. And it's running a completely different approach to the analysis again. So let's see what it decides to do. Now, just to put some of this in perspective, after waiting about 15 minutes for this part, went ahead and it imported all the data. It did, what it did. It said it can't directly execute Plotly plots in this environment. So what it did is it basically said, I'll provide you the code to run in your own environment. Went ahead and tried it. It failed. It said it ran into the technical hiccup again related to handling the Panda series. So there it goes again. It ran into the same problem it had before. It hadn't learned. And it's attempting to run everything again. So I'm going to go ahead and see what it does. If it doesn't function this time, we'll stop here, and we will cover a different approach in the next one when we cover a different type of data set and so on. But I wanted you to get an idea of what some of the limitations were. As you can see, when we go back to all the work we did, there's some errors, human error, but you can see that you can actually take your data in and have it do it. So if I have data but I don't have anything else, I can spend some time doing it. Put this in perspective, I have a version of software now where I can import, on our commercial software, I can import a CSV file and in less than a minute have a full analysis of, say, a transformer, generator, three-stage gearbox, and main bearings in a wind turbine, complete all the mechanical and all the other components in less than a minute. So spending hours or more on this, I would do this if I'm doing research. I would not do this for doing standard work. In any case, let's see if we are anywhere at the bottom. And then I'm going to pause. Here it is. It says basically it went in and it did some stuff. Now we have corrected the data. So they went ahead and did that. They've now set up what the Plotly codes would look like, but it did not run them. So it said, okay, here's the corrected code that you would use in your own, say, Jupyter notebook to import that data. Then here's how you would do the voltage spectrum in Plotly, here's how you would do the current spectrum in Plotly, and here's how you do the kilowatt data in Plotly. So it's not the be-all, end-all. We will explore later, because we've gone over an hour here, but we'll explore another time some of the other tools that they have available in order to look at this data. We'll also take a look at some of the other AI systems that are commercially available that can look at this data. What we're seeing is some of these special systems out there aren't much different than this, and they're actually just data science methodologies in which there's a lot of human tasks. This was purely done this way. If I were doing it, I would be doing it slightly differently, and I have in the past. And I would have some very specific information that I'd be putting in order to get my outputs. So could I do it? Yeah, I could. Could I do it so that I could run things repetitively? Well, I would develop the code here, put it into something else, and then run it that way. You are talking of still a fair amount of time, and again, limitations, as you can see, of the system and the software. So you still can't eliminate all your software programmers. You definitely cannot eliminate your analysts. We'll also take a look another time and utilize it to look at my vibration and ESA data at the same time. With that, thank you very much for following along. Hopefully we haven't had some of the issues we've had in the past with the voice syncing thing. I think that just goes along with Camtasia. But in any case, have a great week, and I'll see you next week.